everyone. Today we're going to be talking about increasing and decreasing trends on the periodic table and how to read them. Okay, one of the first trend we're going to talk about is atomic radius. And atomic radius is defined by the distance from the center of the nucleus to the average distance of the electron cloud, the outer edges of it. And every atom on the periodic table has a different atomic radius. And knowing the trend can help you predict sizes of atoms. Okay, the first thing is as we go from top to bottom on the periodic table, atoms will increase in size. And the reason for that is because as we go into a new period, each row we add another shell of energy. So we're adding those principal energy levels and making the atoms larger. But as we go from left to right, something a little different happens, and that is that the atoms get smaller and smaller. Even though from left to right we're adding protons and neutrons, what ends up happening is that the nuclear force of adding a proton and adding an electron gets stronger and stronger and stronger, and the atom pulls in those outer shells until we get to the next layer and we add a whole new energy level. Okay, so on the periodic table, again from left to right we get smaller, top to bottom we get larger, or if we went right to left we would get larger. So that means on the periodic table the largest atom is francium. Okay, the next thing we'll talk about is ionization energy. And ionization energy is the amount of energy that it takes to remove an electron from an atom. Okay, and we're only going to focus on unstable atoms and not the noble gases. The noble gases are stable. While we have had success at removing electrons from a couple of noble gases like xenon, it does take a tremendous amount of energy because noble gases are very stable. All of the other atoms, not so much. So we can remove and add electrons to them. And on the left of the periodic table, it is easier to pull electrons away than it is from the right of the periodic table. Okay, so it's also easier to pull electrons away from large atoms. And that's because, think of like a magnet. If you have two magnets with opposite ends, the closer they get, the easier they are to attract. But when they're really far apart, not so much. In an atom, you've got a nucleus and you've got shells and shells of electrons way out here. These electrons don't feel very attached to the nucleus, so you can pull them off. But remember, as we go across the periodic table, it doesn't get bigger. That nuclear force pulls in. So the smaller the atom, the easier it is for it to hold on to electrons. So it takes a lot of energy. So that means that if francium is the largest, then fluorine up here in the top is going to be the smallest. Okay, so our smallest atom is going to be the highest ionization energy. All right. And remember, we're not focused on the noble gases. We're only talking about the ones that can remove electrons. Okay. Now, electronegativity is very similar to ionization energy in that they are related. Ionization energy is how much energy it takes to remove an atom. Electronegativity is how easily does an atom take another's electrons. And this isn't something that we can necessarily measure. We can only observe it. It's kind of like saying which thief is the best. Well, how do you quantify something like that? For which atom is best at stealing, it really depends on the ionization energy. Who has the highest ionization energy? If it takes a lot of energy to remove an electron, well, that means that it can also attract electrons pretty well. Okay, And this all has to do with bonding, which we'll get into, and something called ions, which we'll talk about in a few minutes. But electronegativity is a 4.0 scale, 0 to 4.0. Since it's not something that we can directly measure, we can just observe it. So again, the top right with fluorine is going to be our highest electronegativity. It steals electrons the easiest, okay? But we just give it a value of 4.0, all right? And the bottom left is going to be around a 0.1 for francium. So it's an arbitrary scale that is increasing across the periodic table, but it is an observed scale, okay? Now, overall reactivity, this is something that we talk about when atoms are likely to bond and which ones have the highest reactions. I'm sure you've been told before that alkali metals react really violently in water, and that's because they give off their electrons really well. This whole first column, they like to give off their electrons, which causes a reaction. Now, the bigger the atom, the more violent the reaction. So that means that francium is actually going to be the most reactive metal on the periodic table. It's not something that you could ever hold in your hand. It would instantly react with the oil in your hand, or the oxidize with air. And there's not much francium on the planet just because of the half-life that it has, but if you could have a handful of francium, that would be quite a extensive explosion in a pool of water, okay? So it is the most reactive metal. We also call this the most metallic. So on the other end of that spectrum, the most non-metallic is whoever steals electrons the easiest. And if you remember, fluorine is the atom that steals electrons the easiest. So it is the most reactive non-metal, or the most non-metallic. It's so reactive that most chemistry labs don't even use it in studies anymore because it's a very poisonous gas. So your most reactives, most metallic is whatever gets closest to francium. Most non-metallic is whatever gets closest to fluorine, okay? Now, where all this stems from is that all atoms want to have 8 electrons in their outer shell, and we call this the octet rule. So that is their goal. Either they are going to get rid of electrons, or they're going to gain electrons in order to get to 8 octet, okay? And I will show you how that happens and what it looks like in just a minute. But just know that the octet rule applies to only the outer shell. It applies to only that valence shell. And those are the ones that we are most concerned with. Okay? And we use this with something called the electron dot diagrams, also called the Lewis dot diagrams. And when we are drawing Lewis dot diagrams, we are drawing only the valence shell electrons, okay? And these correlate specifically to the groups and families of the periodic table. So for example, let's look here at number 13, aluminum, okay? So we have these major columns. Let's not worry about the transition elements at the moment. We have column 1, 2, 13, 14, 15, 16, 17, and 18, okay? And these columns are going to correlate specifically to the number of valence electrons. Column 1, the alkalis will have 1 valence electron. Column 2, alkaline earth, will have 2 valence electrons. Column 13, where aluminum sits, is going to have 3 valence electrons. And if you look at our diagram here, I've got 1, 2, 3 valence electrons on the outer shell. Okay, all of these in this column are going to have 3 valence electrons. They're just going to have multiple shells, and the valence shell is the outermost. Okay, carbon group will have 4, Nitrogen group have 5, oxygen group 6, and the halogens will have 7 valence electrons, with the noble gases having 8. That's why noble gases are stable. They don't have to lose or gain electrons, and they're not going to react with other elements. Okay, so when we draw our Lewis dots, this is across period 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. When we draw our Lewis dots, we are only drawing that outer shell. Like I said, column 1 has 1 valence electron, column 2, 2 valence, boron is 3, carbon is 4, nitrogen 5, oxygen 6, fluorine 7, neon 8. Now when you draw them, it matters the sequence that you draw them. Okay, you always draw in the 4 quadrants, the northeast, south, and west, and you always draw one at a time before you start pairing up. So if you look at carbon, it has 1, 2, 3, 4 single electrons. Nitrogen that has 5, that 5th electron is paired up with the first one that we started with. Doesn't matter if you start in the north or start in the east, start in the south, just make sure you start in the same place every time when you're drawing them for yourself. So when you get to 6, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. So you always draw 4 singles before you start pairing up. Okay, so again, these are called the Lewis dots, or the electron dot diagrams. And now let's talk about what this means for making atoms stable. We're going to create ions. So an ion is nothing but a charged atom. A charged atom is when we have too many electrons or too few electrons. The protons are always going to stay the same. If we change a proton, we've changed the element. So we're only focused on the electron change. If we lose electrons, then we're going to have an overall positive charge. If we gain electrons, we're going to have an overall negative charge because electrons have negative on them. So we have some names for these. We have cations and anions. So this is an ion. She is negative and unhappy. This is a cation. He is a plussy cat. Your positively charged ions are cations. Your negatively charged ions are anions. Now, where they exist on the periodic table has to do with those valence shells. So first, let's look at a cation. Well, let me talk about ionic radius. Cations are always smaller than the original. Anions are always larger than the original. The cations, the outer layer is removed. The anions, extra electrons are added. So let me show you how this works. Here I have sodium. So sodium has 11 protons and 11 electrons, a neutral sodium atom. It's not charged or anything. Okay, and that 11th electron is 1 valence electron in the outer shell. Okay, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 in the outer shell. Now the question that I always pose is, if you were going to charge your atom to make an octet, you either need to add or remove electrons. In this case, there is 1 electron in the outer shell. So you're either going to add 7 electrons or remove 1. Which do you think is easier? Well, it's going to be much easier to remove 1 single electron. Okay, so when that happens and that electron goes away, we actually lose that entire outer shell, which in turn, just not having that outer shell makes the atom smaller, but it will also shrink due to the nuclear force. There's more protons in the middle, less electrons on the outside, so the atom itself will actually get even smaller. Okay, so cations are always smaller than the original atom, okay? And what this has also done for us is that it has made a charged atom. We have 11 protons and we now have 10 electrons. Well, 11 positives and 10 minuses gives me an overall +1 charge, okay? If you did this with magnesium in the second column, then those 2 electrons in the outer shell, they would be gone. So with magnesium being 12, that would be 12 protons in the middle, and again 10 electrons on the outer shell. So 12 positives and 10 negatives gives me an overall +2 charge, okay? So let's look at anions. Anions get larger, okay? This is chlorine. Chlorine has 17 protons and a neutral chlorine has 17 electrons, okay? And it is a halogen. It is in that 17th column, which means it has 7 valence electrons, all right? So 7 valence electrons in the outer shell is going to allow us to either lose 7 electrons or gain 1 to get to that octet 8. So which one would be easier, lose 7 or gain 1? It would be way easier to gain 1, and that's part of where the electronegativity and the ionization energy come into play. Remember, the higher electronegativity is towards fluorine. So the closer you are to fluorine, the easier you steal electrons. So what chlorine is going to do is steal this 1 electron and put it in its outer shell. Now it has 8, but it went from 17 protons to now 18 electrons. So 17 positive, 18 negative gives me an overall -1 charge, okay? So the other thing that happens is this atom is going to grow. The nuclear force is being pulled out from the electrons. So the atom itself, the ion, is bigger than the original, okay? And that's why that happens with anions. So anions are always larger than the original, and cations are always smaller than the original, okay? The overall trend is still towards francium as a large atom, okay? You can get a little too comparative here when you're talking close between positives and negatives and which one is bigger, but overall your trend is still whichever is closer to francium is going to be your larger ion, okay? Your ionic radius still goes towards francium, okay? And that's about it. Next class we're going to talk about the actual location of electrons in atoms and how to notate electrons. Until then, work together, help each other, and make the world a better place. See ya.